In this episode, let's look at another example of solving linear first order. So here, if you look at this linear first order, it is not in the standard form because you have a 2 here. It's not 1. So let's divide both sides by 2. So the first step, you have to express your linear differential equation in the standard form. So simply in this case, divide by 2. And this is the standard form. Identify the P and Q. So the P is 1 half and the Q is the right hand side. Let's find the integrating factor. U is e to the power integral of P dt. Here T is the independent variable. Sometimes it could be x. Then you take integral with respect to x. Doesn't matter. So here my P is 1 half. So it's e to the power integral of 1 half dt, which is e to the power half t. The integral of half is half t. And do not add any plus c. At this point, your c is 0 because you're looking for one particular function u. So we will choose c to be 0. So that's my integrating factor u. Now I can apply the second step. The second step, my y is given by the integral of uq dt divided by u. So my u goes in place of u, q goes on place of q, and just substitute those information here. So let's do that. So my y is equal to integral of u times q dt divided by u. And now we have to evaluate this integral. So let's do this. So here I'm going to concentrate on the top part first. So let's concentrate on the top numerator. So let's add that down. Let me write this 3 over 2. So let me actually bring this 3 over 2 outside the integral. So here we can use the integral by part. So uh, let's look at here. Let's do the integral by part. So u is t dv. So don't confuse this u with with this u, right? So that's u is for the integrating factor, and this is u like a temporary when we evaluate the integral using the integral by parts. So my dv du is 1 dt. V is the integral of e to the half is 2 e to the power half t. Let's apply the formula. So don't forget this 3 over 2. So I'll probably copy it, otherwise I'll forget. So I have uv. So let me write for the formula is uv minus integral of v du. So let's write that. So uv, so u is t, and so u is t and v is this. So let's multiply them. Minus integral of v du. My du is actually dt. So let's continue evaluate this integral. So so I'll copy the first one. Here I can take out these two outside, and the integral of e to the half t, as the we did this a little bit ago, is 2 times e to the half t. We're going to add plus c at the end of the day. Again, a quick reminder here, right? A very quick way of finding, for example, what is the integral of e to the power 5t dt, right? So that will be 1 over 5 e to the power 5t. So in general, the formula is the integral of e to the power at, where a is a number, is 1 over a e to the power at. So for example, the integral of e to the power 5 over 7t is going to be 1 over 5 over 7. So you can flip it. So you get 7 over 5 e to the power 5 over 7t. And that is exactly what happening. I have to flip this 1/2 and that become 2. Now I can multiply this out. So 2 will cancel out in the denominator. So I get 3t e to the power half t minus 1 of the 2 will cancel out, and then I have to multiply by 3. So I get 6 to the power half t. Okay? And then of course plus c. Okay, I have plus c, and then don't forget the denominator now is e to the half t. So let's write it down what I have. So my y, what I have here is the numerator. Divided by the denominator is e to the half t. So now I can simplify this a little bit. I can distribute this e to the half t. And then c divided by e to the half t, which is actually e to the negative half t. Right there. Okay. And that's my general explicit solution, because y is given explicitly in terms of t. And if you think about this a little bit, sometimes we don't just find the answer, we analyze a little bit in the long run. So many times we're interested what happened to the solution in the long run. So think about t as a time, and this y might represent some solution of our model, right? And you want to know what is the behavior of the model as time goes to infinity, right? In the long run, what is my model looks like in the long run, right? It's a very natural question. So in other words, we want to know what happened to this y as t goes to infinity, right? And as you can see, this part here, as t goes to infinity, this actually goes to 0 as t goes to infinity, because e to the negative half t goes to 0, because the power here is negative half, right? uh, Another way of seeing it, right, you can write it down as c divided by e to the half t, right? And as t goes to as t approaches infinity, this e to the half t approaches infinity, and some constant c divided by infinity, a very large number, approaches 0. So at the end of the day, as t approaches infinity, my y approaches this linear function 3t minus 6. Very interesting, right? So in the long run, the model will be a linear model. You can also see that in GeoGebra as a technique here. So let's go to the GeoGebra. So you start with C, enter, so that will create a bar, and then just enter our function. So it's going to be 3t minus 6 plus c times e to the power negative half t, and then you press enter. So at this point, my c is 1, right? My c is 1. And for c is 1, this is the picture. Okay. It looks like a parabola, but it's not a parabola, of course, right? And and then you can move the c and see how it looks like, right? And you can zoom in, zoom out like that. Okay, excellent. Now let's move my c, and clearly you can see, right? There is a something happening when c is 0, right? When c is 0, you can see it from here, right? When c is 0, this term is gone, right? And you end up with this function 3t minus 6. So when c is 0, if I replace c by 0, right, that is exactly this 3t minus 6. That's the equation of this line, right? Okay. And when c is less than 0, right, and you get a different types of graph now. Okay. So c is 0, kind of a critical value, right? The characteristic of the graph changes at c equal to 0. When c is bigger than 0, I have some type of graph, right? When c is bigger than 0, sorry, when c is bigger than 0, and when c is less than 0, I have some other types of graph, right? It's different types of behavior. Okay. So for example, when c is bigger than 0, right, it's a kind of U shape, right? The function decrease and then increase. And when c is less than 0, when c is less than 0, like something like that, the function is always increasing. So the behavior of our model changes. And of course, when c is approaches infinity, as c approaches infinity, right, uh, this part, because we are looking at when t approaches infinity, right, when t goes to infinity, right? So as t goes to infinity, right, if you go on in this way, right, my t is 900, right, my t is now 1050, and if you look at this part of the graph, is actually extremely close to 3t minus 6. The error is almost ignorable, so you can just really ignore it's not really equal to 3t minus 6, but it's like very close. You can actually see, you can just and plot another function 3t minus 6. Okay, and let's change the color. Maybe I'll choose a different color, blue. Okay, look at here. Do you really see any distinction between the blue and the red, right? If I don't have the blue, that's the red one. So that is this one. And if I select the blue, that is this one, right? It's actually almost on top of the other. Of course, if you zoom in like so much, and then the computer can only do so much, there may be some distinction, but it's like so little, right? And I'm not sure how much zoom we can do. I mean, that's the maximum the GeoGebra can done. So no, there is no that much, there is no difference. The error is very small. Okay. Now if I go here, right, in the beginning there's a big difference, right, in the beginning. But as t approaches infinity, right, they're getting close and close and close. At some point they are literally top of each other. Okay, the error is very small. And always remember, you can do it.